Yeah, so hello, I am audible. Hello, am I audible? If I am not audible, can you please write in the chat box? Hello everyone, is I am audible? Can someone please confirm? If you are unable to turn on your mic, then please write this in the chat box. Hello. Okay, so let's wait for some time so that other people can join. I will start in few minutes. Okay. So I am going to start now. So first of all, I will like to introduce myself. So I am Roushan. I am doing PhD currently now under Prime Minister Research Scholar scheme in the Department of Applied Mechanics at IIT Delhi. So I am going to take a live session in the solid mechanics course, which is taught by Professor Ajit at IIT Delhi. So many of you have already completed the week 1 lectures. So there are 3 lectures in the week 1. That is the first lecture is I think so. Let me check. So week 1 comprise 3 lectures. Is my screen visible to everyone? Can you please confirm? So week 1 has 3 lectures. First one is the mathematical concepts, basically working with vectors and tensor.
শুনতেই পাচ্ছি।
Yes. So is the screen my visible? Is my screen visible to everyone? Okay. So week 1 has 3 lecture, mathematical concepts, working with vectors and tensor. The second lecture is on traction vector, and the third lecture is on stress tensor and its matrix representation. So this lecture, this session is only for discussing your doubts. If you find any doubts in taking the lecture, and also in this session, I will solve some problems which is based on the lecture that you have studied earlier. So first of all, I want to know that how many of you have completed all the 3 lectures of week 1? Can you please confirm in the you can write in the chat box. I can see it. So this session is basically one-to-one interaction. If any of you want to ask something or say something, please unmute yourself and ask with me. I will tell all the doubts which you have. So I suppose none of you has responded. Hello, Gari Patti Fanendra, you want to ask something? Garik Patti. Okay, so uh, I think I suppose everyone has already done the 3 lectures. So I am going to start with the numerical session that is based on the first lecture of week 1, that is mathematical concepts working with vector and tensor. So in this session, I will solve some examples so that you will better understand the concepts which is already covered in the lectures. So in question 1, I will first I will write the question. Then I will explain you how to solve such type of question based on the vector and tensors. So this is you have seen here. So Sij is basically a second order tensor. You see here that it's indicate 2 indices Sij, and AI is a vector. So I have given the component wise, that is each component of Sij represent the component of tensor S, and AI represent the component of vector A. So here we have to find out the component Sij. What is Sij if you want to find it? So first question is evaluate Sij, Sij. So what's the value of this one, Sij and Sij? So here I and j basically means that I goes from 1 to 3 and j goes from 1 to 3, and it indicates the summation. So Sij, as you already taught in the lecture, that if any indices repeated twice or more, then it becomes dummy indices, or we say repeating indices. So here in this one, Sij, you see that here I and j repeated 2 times. So it becomes a dummy indices. That means uh, its summation on ij. So I'm going to expand it. So what it means, Sij means S11 into S11, S12 into S12. This way it will goes on, which basically means that is S11 square plus S12 square plus S13 square plus S21 square plus S22 square plus S23 square plus S31 square plus S32 square plus S33 square. And here in the above matrix you find the value of each component. So after manipulation you find that S11 square is come out to be 1, and S12 square is 0, then 4, 0 plus 1 plus 4 plus 9 plus 0 plus 9, that is 28. So this is a very simple question in which I want to show you how repeating indices operate. So Sij means, that means summation over ij. So I goes from 1 to 3 and j goes from 1 to 3 each time. So in this question, have you any doubt? If you have any doubt, please write in the chat box. I will explain to you. The next question is, suppose I want to find out AM. So this is here also m is repeating twice. So we know that anything repeating, any indices repeating twice is a dummy or repeating index. So it's also indicates summation over a. That means a11 square. That means a1 square plus a2 square plus a3 square, which is nothing but uh, if you take the square of a vector, the a vector component, so 1 square plus 2 square plus 3 square, that is 14. So this is coming out to be 14. The next question is, suppose we have to find out the SMN, AM and AN. So here you see that there is a dummy indices m and n, that is free. There are two free indices m and n, so there is only one component. So it also indicates the summation over m and n in both S and S tensor and A vector. So if we expand this, we found S1n, sorry, S1n, A1, AN. First I will break it over m. So m goes from 1 to 3. So first I will break it through m, that is m1, whether it is 1 or 2 or 3. So I will break it through m. So it becomes S1n, A1, AN, then S2n, A2, AN, S3n, A3, AN. Now after breaking m, then I will break the n component, that is n also goes from 1 to 3. So S11, A1 A1, then S12 A1 A2, then S13 A1 A3. Similarly, in the second term, S2 and S21 A2 A1, S22 A2 A2, S23 A2 A3. And in the same way, the third term also expand S31 A3 A1 plus S32 A3 A2, S33 A3 A3. So here only mathematical operation is now remaining. So if you calculate this one, so you will get 1 plus 0. I am writing here each term component. So 1 plus 0 plus 6 plus 4 plus 12 plus 9 plus 0 plus 27, that is 59. So this is the final answer that you will get after solving this one. So here I am basically trying to explain how repeating and dummy indices means. If suppose I want to write, there is another question. So AI, what it means? What is AI? So here only one indices come, that is I. That means it's a free indices. It's not meaning summation. So it basically goes from A1, A2, and A3. So there are three components of A vector, that is A1, A2, and A3. And every vector represented in a matrix form in this way. And you also know in the lecture, through the lecture, that tensor is independent of the coordinate system. Suppose if I write it in this way, A. So that tilde that underlines shows a vector. So a single small I have shown A through a small letter, and underscore underline it's shown with a tilde vector. So it basically represents a vector, and it has three components. If we want to write in the component way, so it shows in this way. A component is A1, A2, and A3. The tensor is independent of coordinate system. However, if we write its component, so it changes from one coordinate system to another coordinate system. So suppose if we want to write in different bases, if A in E1, E2, and E3 coordinate system, the component is suppose 1, 2, 3. So its component in suppose in another coordinate system, that is E1 hat, E2 hat, and E3 hat. The component is different. In the here the component is different. So we don't know unless we want to know the component how it relates with the E1, E2, E3 coordinate system. So we need to relate with it E1 hat, E2 hat, and E3 hat, how it related with a E1, E2, E3 coordinate system. Then we can find out that component of A vector in E1, E2, and E3 coordinate system. So this basically means that any vector, a first order tensor, or you say, is independent of coordinate system. That means it never changes from one coordinate system to another. However, its component will change if we change the coordinate system. That is our Cartesian system. If we take the value of A, component of A in Cartesian system, that is in E1, E2, E3, then its value is 1, 2, 3 suppose. And if we want to change the basis, suppose in E1 hat, E2 hat, and E3 hat coordinate system, its value changes. So this indicates that a vector component has different value in different coordinate system. Uh, Basically, this is also, a vector is also termed as a first order tensor. So in the general way, a tensor is independent of coordinate system, and here you see that Sij. So it denotes that Sij, that means S tensor is independent of coordinate system. However, its 9 component, that is I goes from 1 to 3 and j goes from 1 to 3, represent 9 component in some coordinate system. If we want to write in different coordinate system, the value of each component changes. So is there any doubt, till now? Okay. If anyone of you wants to ask something, please write in the chat box, or you can say directly by muting your mic. So the next question is, suppose we have a tensor, we have a second order tensor. A and another second order tensor B, such that A is equal to A transpose. That means this is a symmetric tensor and B is equal to minus of B transpose. That means it is a skewed symmetric tensor. So we have to prove that the product of a symmetric and a skew symmetric tensor is 0. So this is a second order tensor. A is also second order tensor and B is also a second order tensor, and we have to prove that product of A and B is 0, such that A is a skew symmetric tensor. A is a symmetric tensor and B is a second order skew symmetric tensor. So how to prove this? I will explain it. So here A is a second order skew symmetric tensor. So we can write component of A in this way, Aij, and it's a symmetric tensor. So we can also write it as Aj. That means transpose of A is equal to A. And B tensor is a skew symmetric tensor. So we can write in this way, Bij is equal to minus of Bji, that is minus of B transpose. And if we multiply A and B with its component, that is Aij into Bij, what we get? So Aij is Aji and Bij is minus of Bji. As you see here that J and I both are repeating twice. So it basically represent a dummy indices or repeating indices. So we can change, we can give any indices to it. So we can change their form. That means we change the indices j with I and I with j. We can do this in a dummy indices. So it becomes A I j and B I j. What I do is I change the indices j with I and I with j. So it becomes minus of Aij and Bij. So next we do the operation. So minus, when it goes from minus here, that means this term, put it back to the left hand side, we get Aij Bij plus Aij Bij is equal to 0. That means Aij Bij is equal to 0, which basically means A into B tensor is equal to 0. So it proves that the product of a symmetric and skew symmetric tensor is 0. So all of you understood it? If you have any question, please ask. Unless you don't understand, directly coming to the meeting and seeing the lectures will not help you. So please ask if you have any doubt in any way. I am assuming that you have done all the lectures of the week 1, and if you see the lecture, you will find all the things already taught there. So I am doing only some questions here. So move on to the next question. So we have to evaluate delta ij, delta ik, and delta jk. So what's the value of this one? So you have already seen the lecture that delta is basically canonical delta function. So delta is canonical delta. We call it canonical delta, and it means that if we see the component of it, del ij, so its value is 1 if I is equal to j, and its value is 0 if I not equal to j. That is, for the same value it gives us 1, and for the different value, if I is not equal to j, we will get 0. So based on this, we have to evaluate what is the value of del ij, del ik, and del jk. So del ij, del ik, del jk is equal to, you see here that I is repeating 2 times, j is also repeating 2 times, and k is also repeating 2 times. Sorry, yeah. So I have only get it. So I is repeating twice, j is also repeating twice, and k is also repeating twice. So if we evaluate it, we will get, as here ij, del ij is repeating with del ik, so k is replaced with k. That means it becomes del kj, del jk. So first we are evaluating this one. Then also you can see that k is also repeating twice, and j is also repeating twice. So we can replace this with k with j or j with k. So we are replacing k with j, so it becomes del jj, and j goes from 1 to 3, and here j is repeating twice. That means it shows summation over j, so it becomes del 1 1 plus del 2 2 plus del 3 3. And from the definition of canonical delta, if I is equal to j, we will get the value is 1, and if I not equals to j, it becomes 0. So here I equal to j in all the 3 terms, so it becomes 1 plus 1 plus 1, that is 3. So the value here is coming out 3. Is it clear to everyone? Okay. I'm assuming that it has clear to everyone. So I will move to the next question. So there is a one function which we called already you have seen in the lecture that tensor product is denoted by this one, dyadic, and vector product is denoted by this one. So if we write a tensor product, it is denoted by dyadic, and if we write a cross product, we have to show it in this way. Okay, so based on this, we have a one question, that is we have to show which question number is this? Is question number 4. So in this we have to show a tensor product B. Here single tilde denotes a vector, and if I wrote any letters in small letter with a single tilde, it represents a vector, and if I denote a letter with a capital one with a double tilde, it denotes a second order tensor. So here vector A tensor product vector B multiply with vector C tensor product vector D is equal to vector A tensor product vector D and vector B dot C. So this is not a question, this is basically a mathematical description, the definition of a single contraction. This is called, that is a single contraction B. Suppose this is a already if we do a tensor dyadic product of the two vectors, we get a second order tensor. So tensor A in the single contraction tensor B, we get A vector tensor product D into B dot C. So this is a definition of a single contraction. And if we want to do double contraction, suppose we have to find out A tensor product B double contraction C tensor product D is equal to, this is actually single contraction reduces the order of the tensor. So here you see that it becomes a second order tensor, the result is a second order tensor, and double contraction reduces the order of a tensor twice. So it becomes a scalar quantity, that is A dot C B dot D. So here A is dotted with C and B is dotted with D. So this is a definition of a double contraction. This is single contraction. Of second order tensor, single contraction, and this is double contraction. This is also called multiplication of two second order tensor, and this is a double contraction of two second order tensor. If anyone asks you what is the multiplication of two double second order tensor, so it means that it's a single contraction with two vector within two tensors, and double contraction means it's gives us a scalar quantity if we double contraction of two different second order tensor. So based on this formula, I want to solve one question. So this is question number 4 basically. This is for your reference. You can use it anywhere if you want to do any operation within tensors. So question 4 is, we have to prove that A tensor times A vector tensor product B is equal to A tensor times A vector tensor product B. So we have to prove this one, that A times A vector daddy product B is equal to tensor A times vector A daddy product B. We have to prove this one. So for this, we need some information how tensor operates with a vector. So first of all, and one thing I like to mention here, that it will not become this one, A times A vector tensor product A times B vector. This is not the correct answer. So whenever you have a double second order tensor multiplied with a second vector tensor product vector, so it will get we will get tensor A multiplied with vector A daddy product B. So we have to prove this. So I am going to solve this question. So tensor A can also be written in component form in this way. Aij is the component, and if we write in a tensor form, so it will write in this way: Aij Ei tensor product Ej. This is multiplied with vector A tensor product vector B. So here, from the above definition of single contraction, you see here A tensor product B times C tensor product D gives us A tensor product D times B dot C. That means outer one is this one, A and D get tensorly multiplied, and inner one is dotted. So here also we have 4 vector and 2 tensors multiplied with each one, that is Ei tensor product Ej times A tensor product B. So this is the component only. Aij is only the component, and here is the complete tensor. Ei tensor product Ej times A tensor product B. So Aij, and we are using the above formula, that is, so this one is dotted, that is A dot Ej, Aij Ej dot A times Ei tensor product B. So we write the above one in this way. Next, if you see it, you find that Aij and Ej dot A. What is Ej dot A? It's basically a jth component of vector A, and Aij is component of tensor A. So if we write, suppose if we write this one, A into A, that means tensor A into vector A. What it gives? Aij Ei tensor product Ej times A. So it gives Aij, and you see in the lecture that this 2 is dotted with each other, that is J and A are dotted with each other. So J and A is dotted, so Ej dot A into Ei. So this way. So if we compare this one, if we compare this with this one, we get tensor A multiplied with vector A tensor product B. So we have got what is mentioned in the theorem, that is, so basically what we prove, A tensor A times A tensor product B is equal to tensor A times vector A daddy product B. So this is the final result which we want to get. Now we move on to the next question, question number 5. The next question also based on the above formulation. So in this question, we have to prove that A tensor product B times A is equal to A tensor product A transpose into vector B. So this is similar to above problem, but here the tensor A is post multiplied by vector A dyadic vector B. So in this case, A comes inside along with vector B with a transpose. So we have to prove this one with the above formula. So now I'm going to solve this question. So the solution is, so here A tensor product B into Aij, we can write in this way: Aij, the component of vector tensor A can be written as Aij, and if you want to write in tensor, so Aij Ei tensor product Ej. Okay, and here Aij we can we can put it outside from the tensor product, so it becomes A tensor product B times Ei tensor product Ej. So as from the above formulation, we know that this 2 1 is dotted, that is B dot Ei, and A is tensor product with Ej. So it becomes vector A tensor product Aij into B dot Ei times Ej. So here what I have done is Aij is a component, is the component of each component of the second order tensor. So we can move it anywhere in the operation, and B dot Ei gives us a scalar quantity. So we can also move it anywhere, and here A vector A and Ej dyadic with each other. So here it also show here that vector A dyadic with Ej, because this is a vector and inside is the component. Aij is the component of each component of the second order tensor, and B dot Ei gives us a scalar quantity. Next is vector A tensor product Aij Ej into B dot Ei. We can write in this way also: vector A dyadic product Aij, and this one can be written as Ej tensor product Ei times B. So if we see it, Ej tensor product Ei times B gives us, this two is dotted with each other. So Ej into Ei dot B. So Ei dot B, you can see here that B dot Ei same as Ei dot B into Ej. So we can write in this way: Ej tensor product Ei times B. A tensor product, you can call it tensor product or dyadic product. So Aij ej tensor product ei into B. And what is this? So this is basically A transpose, tensor A transpose, because A is given by Aij Ei tensor product Ej, and A transpose is given by Aij Ej tensor product Ei. So this is basically A transpose, which gives us A dyadic A transpose into vector B. So this proves our result that is written above. So here we conclude that vector A tensor product B times tensor A is equal to vector A tensor product A transpose into B. So this is the result of the above proof. Now we move on to the next question, that is question number 6. So before going to question number 6, I want to explain one symbol, that is alternator or permutation symbol. So it denotes as epsilon, and it means epsilon ijk. Component of epsilon is ijk, and it becomes 0 if any one of the two indices are same. If any two indices are same. So this all the questions solved here based on the lecture number 1, that is preliminary concepts, mathematical concepts based on vectors and tensors. So epsilon ijk will become 0 if any of the two indices, whether it's jk, ij or ki, is same, then it becomes 0. It becomes 1 if all the three are different. If all the three indices are different and in cyclic order. That means clockwise direction. So I, j, k. If in this way we can write, if the indices forming this way I, j, k type, then the answer is 1, and it becomes minus 1 if all the component, all the three indices are different but not in cyclic order. That means if we if we want to know the value of epsilon 1 1 1, so here all the three indices are same, so what it gives us, it gives us the value of 0. If we want to know the value of epsilon 1 2 2, here also two indices are same, it also gives us 0. If you want to know the value of 1 2 3, so here you see that 1 2 3 are in cyclic order, so it gives us 1. Similarly, epsilon 2 3 1, so 2 3 1 is also in cyclic order, so it also gives 1. However, if you want to know the value of epsilon 1 3 2, so this is not in cyclic order. You see here that 1, after 1 3 comes, then 2, so it's not in cyclic order, so it gives us the value of minus 1. Similarly, epsilon 3 2 1 is also not in cyclic order, so it gives us a value of minus 1. So this is the meaning of alternator or permutation symbol, which basically denotes the value of 0 1 and minus 1. It takes three value, 0 1 and minus 1. So based on this concepts, I want to show you one example, or you say problem, that is problem number 6. So the question is, what is the value of epsilon ijk and epsilon ijk? Okay. So before going to solve this question, I want to know you the formula for this one. If two different permutation symbols are multiplied with each other, what is the value? So if epsilon ijk and epsilon pqk is multiplied with each other, then it gives us delta ip. So I is multiplied, I is coming with p, delta ip, then delta jq, j is coming with q, minus delta iq into delta jp. So this is the formula if we multiply two permutation symbol. So this can be written in this way. This two multiplication can be written in this way also. So based on this formula, uh, we have a question here. So epsilon ijk into epsilon ijk, what is the value of this one? So I am going to solve this question. So epsilon ijk is equal to, so based on this formula, it gives us del ii, then del jj minus del ij, del ji. So here the first component is del ii, how it comes. So I is multiplied with I, so I del ii, then del jj, then minus with reverse order, minus with reverse order we get del ji, then del ij. Now what's the value of this one? So I already discussed above the meaning of Kronecker delta. If the indices is same, it gives us a value of 1. So 1 into 1, sorry, if indices is same and I goes from 1 to 3, so here indices is same and it, which means it's summation over I, so it gives us del 11 plus del 22 plus del t3, that means 3. Similarly, del jj is also a summation over j, it's a dummy indices, so it gives also a value of 3, minus del ij and del ji. So here you see there are two different tensor component of a tensor, and I is repeating twice and j is repeating twice, which can also be written in this way, is equal to, this can also be same as del jj, or we say del ii. You can write it anyway. So this becomes 9 minus del jj. What is del jj? So it's summation over j, or del I is also summation over I. So it gives del 11 plus del 22 plus del t3, which is 3. So it becomes 9 minus 3 is 6. So the value of epsilon ijk and ijk is 6. So this is the meaning of permutation symbol, or alternator, or permutation symbol. So now we will move on to the next question, that is question number 7. Please let me know if anyone have any doubt or you want to ask something. Please raise your hand or unmute yourself so that I can listen you. So the next question is, we have to prove that vector A cross B cross C is equal to A dot C times B minus A dot B times C. So this is a question which you already know, I think. So we have to prove this one based on the permutation symbol, using the permutation symbol. So we have to prove this one using permutation symbol. So here A cross B cross C is same as A dot B times C minus A dot B times C. So we have to prove this using permutation symbol. So before going to solve this, I want to tell you something, that if A cross B, if we want to written in initial form, it can be written in this way: epsilon I j k aj bk into ei. So in initial notation, cross product of two vectors can be written in this way. So cross product of two vectors can be written in this way. Now I'm going to prove the above formula, that is A cross B cross C is same as A dot C times B minus A dot B times C. So we have to prove this one. So I'm going to solve this question. A cross B cross C. So what it gives, I am going to write this vector product, vector triple product in initial notation. So A in initial notation can be written as AM EM cross with B cross C in initial notation can be written in this way, which I show you above. So epsilon IJK BJ CK EI. Okay, and epsilon IJK we can we can take it back from outside, because it's a component, it shows component, it's not so any vector or tensor, so we can get it outside. So epsilon ijk into am bj ck, and what is left behind, em cross ei. Okay, then epsilon ijk I written as it is am bj ck, and what is em cross en, em cross em cross ei. So it can be written as in permutation symbol, using permutation symbol, epsilon nmi into en. So it can be written in this way. Please raise your hand if you have any doubt. I am solving this question. In between, you can also ask if you have any doubt. So epsilon ijk am bj ck into, what I do is I put it in front, epsilon nmi am bj ck into en. Okay, epsilon here ijk, so we can reverse their order in the cyclic way. So ijk is same as jki is same as kij. So I I have written this in this way: epsilon jki epsilon nmi am bj ck into en. And what is epsilon jki, epsilon nmi? It's a multiplication of two permutation symbols, so it get we will get del jn, j is go with n, then k goes with m, into del km minus, then in the reverse order, minus del j m into del k n times am bj ck into en. Okay, now del jn del km I have multiplied the inner terms with outer terms, so we get del Jn into del Km Am Bj Ck into En minus with del Jm del Kn Am Bj Ck into En. So what we will get is, so here you see K M is repeating index, so del Km Am becomes Ak, so Ak. J is repeating also, and del Jn Bj becomes Bn, then Ck into En minus, similarly this one Am and del Jm, so M is repeating twice, so it becomes Am del Jm becomes Aj. Similarly, and K is repeating twice, so del K and Ck. So Ck del Kn becomes Cn. So Aj, Bj, Cn into En. Here we will get, and now we can see that AK, Bn, Ck. So AK, Ck. What is, if you want to see the dot product A dot C, so we get AI, Ci. Okay. So here also we get AK, Ck, A dot C, and Bn En is basically denotes a vector, so B times B minus, similarly in this way also Aj Bj denotes A dot B times Cn En denotes a vector, that is Cn, sorry, C. So we have proved that triple scalar triple product, sorry, vector triple product gives us A dot C into B minus A dot B into C. So we have proved that A cross B cross C is same as A dot C times B minus A dot B times C, using the permutation symbol and Kronecker delta. Okay, so we have proved in this question. Now we move on to the second question, next question, that is question number 8. So before going to the next question, which is based on the next lecture, that is traction vector. So first of all, I would like to uh, say something that this above question is based on the mathematical concepts based on the vector and tensor. So I have solved some questions based on the vectors and tensors. So anyone who have joined late, I want to briefly explain you above. So I am starting the session with a question. I have given one question, that is one is a second order tensor and the second one is vector, and I write all the component of it, and I solved it in different way, that if you want to know what is the value of Sij, then I solve this one. You can also see that lecture after this session. NPTEL team will upload the lecture recording, recorded lecture in the YouTube also, and in their website also. So you can also go back to this lecture and see what I have tell so far. So this is the question based on the matrix and tensor multiplication, the first question. The second question is based on, if we have to prove that the product of a second order tensor to second order tensor is 0, such that the first tensor is symmetric and the second tensor is skew symmetric. So we have proved using addition notation in question number 2. Then question number 3, I explain first the Kronecker delta, meaning of Kronecker delta function, and then after using that formula, I have solved one question based on the Kronecker delta, that is question number 3. Then I move on to the next question based on the dyadic and tensor product. So in this question, I have solved one proof and explained some formula based on the tensor product. So question number 4 and question number 5 I solved based on the tensor algebra. Then I explain you I explain you about the alternator or permutation symbol, which is nothing but epsilon, which is denoted by epsilon, and it has 3 values. It will take 3 different values, 0, 1 and -1. So in this I will explain, I had explained you that if any two indices are same, then it gives us a 0. If all the 3 indices are different, and it's arranged in a cyclic order, it gives us 1, and if all the 3 indices are different but not in cyclic order, it gives a value of -1. And based on this permutation symbol, if we multiply two permutation symbol with each other, we will get this relation. That is, if we multiply two permutation symbol, product of two permutation symbol gives us del ip del jq minus del iq del jp, which is same as epsilon ij epsilon pqk. Based on this formula, I have solved one question, that is what is the value of epsilon ijk and epsilon ijk. Then I solved next question, which is also based on the permutation symbol, that is a cross b cross c, and it gives us a dot c times b minus a dot b times c. So this is nothing but vector triple product, and I have to solve it using permutation symbol. So before going to solve it, I had explained you the cross product of two vector in permutation symbol. If you want to write in initial notation, it can be written as epsilon ijk aj bk into ei. After that, I have solved this proof. So it's solved in a similar way using relation of permutation symbol and cross product. So at last, I have solved this question of scalar vector triple product. So I move on to the next question, which is basically based on the traction concept. So first I will write the question. So question number 8 is traction on how many planes are needed to completely define the stress tensor at a point. So in this question we have options. The first option is 1, the second option is 2, and the third option is 3, and the fourth option is none of these. So in lecture also you have seen that in the lecture it has been taught that we need 3 different planes, at least 3 planes are needed to completely define the stress as at a point. So in the lecture also you have seen the stress representation that is given in this way. So stress tensor at a point, that is sigma, can be defined in this way. Sigma of x at a point x can be written as summation over I equal to 1 to 3 Ti tensor product Ei. Okay. So this is a stress tensor. So if we want to find, if we want to define the stress as at a point, that is, if we want to find out the stress tensor at a point, we need to know the traction on three different planes at that point, which is given by Ti tensor product Ei. And in this way, we can calculate the stress tensor at a particular point. And you already know that at a point, suppose there is a body and there is a point. So at this point, how many planes are possible? We have infinite number of planes at a point. And if we know at least, and if we know the traction at a point at three different planes, we can define the stress at that point. So there are infinite number of planes at a point, and we need to know the value of the traction at three different planes to find out the stress tensor at that point. So this is the answer, that is 3. We need at least 3 plane traction on at least 3 planes to completely define the stress at a point. Okay. Now we move on to the next question, question number 9, which is also based on the traction. This can you can see this formula also in the lecture sheet, the lecture, or that is lecture number 3. This question is based on lecture number 3 of week 1. The next question is question number 9. So first I will write the question. Suppose the traction vector on 3 perpendicular planes with normal A, B, C are as follow. So we have given traction vector on 3 perpendicular plane whose normal is along A vector, B vector and C vector respectively. So what is the traction? So traction on that plane is given by traction on plane A. Traction on plane A with normal along A. So it is given by TA, which is given as -1 E1 plus √3 E2. Traction on plane B is given as √3 E1 plus 1 E2. And traction on plane with normal C is given as 10 E3. Okay. So next I'm going to explain what's the question actually. So here plane A and plane A normal, plane B normal and plane C normal is defined as A is given by 1 by 2 √3 E1 plus E2. B is given by 1 by 2 minus E1 plus √3 E2, and C is equal to E3. Okay. Where E1, E2, E3 are the standard bases in Cartesian coordinate system. In Cartesian coordinate system. So first of all, the first question is write down the corresponding strain tensor, sorry, stress tensor. Write down the corresponding stress tensor. Okay. So here we have to write the stress tensor with the particular, with the given traction vector. So as I earlier show you the formula of a stress tensor, that is sigma of x is nothing but summation over Ti tensor product Ei, where summation goes from 1 to 3. That is, we need to know the value of traction on 3 different planes at a particular point. Okay. So first we have to write the tensor form. We have to write the stress tensor. So sigma is given, which is a second order stress tensor, is given by Ta summation over I is equal to 1 say 3 Ti tensor product and sorry Ei. And if we know the traction at 3 different planes, so it is given by summation Ta tensor product, and we have 3 different plane A, B and C. So it can be written as Ta tensor product A summation Tb tensor product B plus Tc tensor product C. So the stress tensor can be written as in this way: Ta tensor product A plus Tb tensor product B, Tc tensor product C, where A, B and C are the corresponding plane of the traction vector where traction is defined, and A, B and C traction sorry plane defined by this one A, B and C. So it is defined in this way. So this is the corresponding stress tensor, and we have to solve the next question, that is question number B, 9B. So in this question we have to write down the stress matrix in the coordinate system of both A, B, C coordinate system and E1, E2, E3 coordinate system. So we have to write the stress matrix. What is the value of a stress matrix in both the coordinate system, that is A, B, C coordinate system, and what is the stress matrix in E1, E2, E3 coordinate system. As I already told you earlier, that the representation of a stress tensor depends on the coordinate system. That is, if we want to write a stress tensor in E1, E3, E2, E3 coordinate system, the coefficient, each coefficient changes if we change the coordinate system. However, the stress tensor remains the same. It does not depend on the coordinate system. That is we can say, we obviously say that stress tensor is independent of coordinate system. Even any tensor is independent of coordinate system. So here, uh, so what is the how to calculate the stress matrix in both the coordinate system? So I will explain now. So first one, we have to write stress tensor, component of a stress tensor in E1, E2 and E3 coordinate system. Okay. So here you already see that the traction on plane A in E1, E2, E3 coordinate system is written here. Traction on plane B in E2, E3 coordinate system, E1, E2, E3 coordinate system is written here, and traction on plane C in E1, E2, E3 coordinate system is written here. So as you see in the lecture that each column represent each plane. Okay, each column of a stress matrix represent each plane where traction is defined, and each coefficient of each column represent the direction of traction vector in that particular direction. Okay, so here TA, TB and TC are three different traction defined on three different planes, and in E1, E2, E3 coordinate system it can be written as -1. What is the traction on plane A in E1, E2, E3 coordinate system? Minus E1 plus root 3 E2, minus E1 plus root 3 E2. Along E3 direction there is no coefficient, so it's 0. Then traction on plane B along E1 direction is, the coefficient is root 3. So we write here root 3. Along direction E2 is coefficient is 1 and along E3 is 0. So along E2 direction is 1 and along E3 is 0. Similarly, traction on plane C along E1 direction is 0, in E2 direction is 0, and along E3 direction is 10. So this is the stress matrix in E1, E2 and E3 coordinate system. Okay. Now we want to know the value of the coefficient of a stress tensor in A, B and C coordinate system. So as per the definition of stress tensor, each coefficient on the first column can be defined as TA dot A, TB dot B, TA, sorry. So TA represent the traction on plane A, TA on C, and we want to know the value of the coefficient of traction on plane A along A direction, along B direction and along C direction. Similarly, the second column represent traction on plane B, and we want to find out the traction on plane B along A direction, so it becomes TB dot A, along B direction it becomes TB dot B, and along C direction it becomes TB dot C. Similarly, traction on plane C along A direction given by TC dot A, along B direction TC dot B and TC dot C. So we have know the value of TA and A vector, similarly TB, TC and A, B and C vector. So simply here we have to do the dot product of each traction vector with the direction vector. So TA dot A gives us minus root 3 by 2 plus root 3 by 2, that is 0. Similarly, TB dot B gives us TB dot A. So first of all, I will calculate traction on plane A along A, B and C direction. So TA dot B, so plus 1 by 2. Here you see that. So TB is root 3 plus 1 E2, and if it is dotted, TA is minus 1 E1 plus root 3 E2, and when it is dotted with B, so it gives us 1 minus 1 into 1 by 2 plus root 3 into root 3 by 2. Okay, so it becomes plus 1 by 2 plus 3 by 2, which gives us 2. Similarly, TA dot C become 0. In the same way, traction on plane B along A, B and C direction will give us 3 by 2 plus 1 by 2 is equal to 2 on direction B. Along direction B, the component of traction B on along B direction gives TB dot B, which is nothing but minus root 3 by 2 plus root 3 by 2, that is 0. Similarly, TB dot C gives us 0. And the last one is traction on plane C along A, B and C direction, which is given by TC dot A is equal to 0, TC dot B is equal to 0 and TC dot C is equal to 10. So this is the value of the traction on plane C along A, B and C direction. So this is the final component, each component of the stress matrix in A, B and C coordinate system. Okay. Now we know the value of each coefficient, that is TA dot A, TA dot B, TS dot C, TB dot A, TB dot B, TB dot C. So we can simply write it in the stress matrix. So we will get the stress matrix in A, B and C coordinate system is equal to 0. So here it is TA dot A. What is TA dot A? 0. Then the second row is TA dot B, which is 2. The third row first column is TA dot C, which is 0. Then first row second column is TB dot A, which is 2. Second row second column is TB dot B, which is 0. Third row second column is TB dot C, which is 0. Third, then third row, what is this? First row third column TC dot A, which is 0. Then second row third column, which is TC dot B, which is 0. And the third row third column is TC dot C, which is 10. So this is the stress matrix in ABC coordinate system. Okay. Now we will move on to the next question. So here I will explain here briefly that what we have done. So in this question, we have given a traction vector on 3 perpendicular plane with normal ABC. Okay. So here traction vector on 3 perpendicular planes with normal ABC is given by this one, TA, TB and TC, where A is given by this one, B is given by this and C is given by this one. We have to first calculate, write down the corresponding stress tensor. So according to formula, as you were seeing the lecture, that it is given by summation over I equal to 1 say 3 Ti tensor product EI, and in this way we can represent the stress tensor. The second question is, write down the stress matrix in the coordinate system of both ABC and coordinate system and in E1, E3, E1, E2 and E3 coordinate system. Okay. So here in E1, E2, E3 coordinate system, it can be written in this way, and in ABC coordinate system, it can be written in this way, that is TA dot A, TBA dot B, because we have to find the component of traction on plane A along A direction, component of traction vector A, so traction vector on plane A along B1 direction, B direction, and similarly traction vector on plane A along C directions. So it can be written this way, TA dot A, TA dot B and TA dot C. Similarly, second column represent traction on B plane and third column represent traction on C plane. So in this way we can find the stress matrix in different coordinate system. So the next question is question number 10, which is the last question of this session. So this is a This is basically the second last question. So this is a basically optional question, multiple choice question. So here the question is, which is correct statement? This question is based on the above question only. So the first option is traction vector on C plane is along E3 direction. The second option is component of stress tensor is independent of coordinate system. And the third question is component of stress tensor is dependent on the coordinate system. Dependent on the coordinate system. Okay. And the last option is none of these. So coming to the first option, traction vector on C plane is along E3 direction. So first we can check here that traction vector on C plane. So this represents the traction vector on C plane. Okay. So this is along E3 direction, which is correct because the two component along E1 and E2 direction is 0, and there is only component along E3 direction. So traction vector on C plane is along E3 direction is correct. Component of stress tensor is independent of coordinate system. So if we, that means if we change the coordinate system, so the component of stress tensor also does not change. This statement generally means that if we change the coordinate system, their component does not change. So is it correct or wrong? So I already told you that if we change the coordinate system, component also changes. So this statement is wrong. Component of stress tensor is dependent on the coordinate system. So this is the right option. So these two option out of the four are correct. So this is a question based on the above problem. So this will clear a doubt that stress tensor and the component of stress tensor are different thing. If you want to know the stress matrix is the representation of the stress tensor, and that is not actually the stress tensor, and it changes if we change the coordinate system. Now I am going to solve the last question of this session, question number 11. So this question is the component of stress tensor, the component of the stress tensor at a point P are given in appropriate units by sigma. So here component of stress tensor sigma is given, that is sigma is given by 1, 2, 3, 2, 4, 6, 3, 6, 1. Okay. So here the first question is traction T at point P on the plane normal to E1 axis. So here we have to find the traction T at point P on the plane which is normal to even axis. That means that plane normal is along even axis. So what is the traction? We have to find that traction value. So we know from the lecture, you can also see that traction is given by, in terms of stress tensor, sigma into n, where n is the plane normal. Okay, so the n is the plane normal and sigma is the stress tensor. So if we find out the traction in component form, we can written in this way: component of sigma multiplied by component of plane normal. So here sigma is stress matrix in E1, E2, E3 coordinate system is given in this way: 1, 2, 3, 2, 4, 6, 3, 6, 1. And as given in the question itself, that the plane normal is along E1 axis, which is nothing but its component in E1, E2, E3 coordinate system is given by 1, 0, 0. So the component of plane normal in E1, E2, E3 coordinate system is given by 1, 0, 0 because it is along the E1 axis. So if we calculate this matrix multiplication, we will get 1, 2, 3. So the traction vector, this is basically the component of traction vector. So the traction vector is given by E1 plus 2E2 plus 3E3. So this is a traction vector at a point P on the plane which is normal to E1 axis. The second question in this problem is traction T at point P on the plane whose normal has direction E1 minus E2 plus 2E3. So this is a question that we have to find the traction T at point P on the plane whose normal has direction E1 minus E2 plus 2E3. Okay. So here I would like to mention one thing, that the n, that is the unit normal vector. This is not a normal vector, this is a unit normal vector. And here it is mentioned that the normal has the direction E1 minus E2 plus E3, 2E3. So we need to, so to find out the traction vector T, first we have to find out the unit normal vector of that plane. So the unit normal vector along direction is given by n is equal to E1 minus E2 plus 2E3 upon magnitude of E1 square, that is 1 square plus 1 square plus 2 square, which is nothing but 1 by root 6 E1 minus E2 plus 2E3. Okay. So this is the unit normal vector along that plane. So we know the value of the normal vector to that plane. Now we have to find the traction vector at that point, that is point P, which is given by T is equal to sigma into n. And in component form we can write it as Ti is equal to sigma ij nj. Okay, which is in matrix form can be written as sigma ij is known here. So what is this? 1 by 2, 1, 2, 3, 2, 4, 6 and 3, 6, 1. And nj we have calculated above. So 1 by root 6 into 1 minus 1 and 2. So it will give us 1 by root 6, 5, 10, minus 1. So the traction vector in this case is given by 5 by root 6 E1 plus 10 by root 6 E2 minus 1 by root 6 E3. So this is the value of the traction on the plane whose normal has direction E1 minus E2 plus 2 E3. So this is the question based on the traction vector and the stress tensor. So this I have solved around 11 questions, which is a very good question through which you can clear your doubt. So to better understand, actually this problem is based on the lecture that you have earlier listened, that lecture 1, 2, 3. So if you have not taken that lecture before, so first go to that go through that lecture, and then come back to this session. It will understand you better. And moreover, the recording of this session is also been given to you later on by the NPTEL team. So don't worry if you miss something here. And if you have any doubt, please write in the discussion forum. And one thing also I would like to mention that on a weekly basis there are 2 sessions which is conducted by 2 different instructor. So I will conduct this session based on each week lecture on every Friday. So if you want to, if you have missed something or you have remained some doubt based on week 1, you can also join in the coming Tuesday lecture, coming Tuesday session, which is which will be taken by some another instructor. So this is at all the complete lecture, complete live session, which is basically a doubt solving session, or you say doubt clearing session. So this is all about lecture session 1 of week 1. So the next lecture of mine will be taken in the next coming Friday, which is based on the week 2 lectures. So first of all, I would like to request all of you that please go through that lecture before coming to this session, because it will understand you better. If you don't see that lecture before doing this session, then it will difficult for you to understand in a better way, because this course uh, is only understood when you do the lecture very seriously. So I urge everyone that please go through lecture first and then coming to this session, then you will understand in a better way. So that's all about this session today. I am going to wrap up this session. So thanks for coming to this session, and thanks to everyone. Okay. So that's all. Thank you. You may leave the meeting. So thank you.